thank you very much for the introduction. We'll make it more technically involved. Thank you very much for coming. Do I have to turn this on? Is it already? Okay. Yeah, thank you very much for coming. And thank you to Ivan and Julia and Guillermo and Pavel and Chris for inviting me and for organizing such a great conference. Pavel kind of set it up for me yesterday, saying that today is going to be about stable categories, so it will be about stable categories. And I think there are two trends I'll try to follow. My category will be symmetric. That was a very hard decision, but I guess it had to be. And there also seems to be sort of a soft rule that you have to refer to deline at some point. I'll do that. But I will also deviate from something else that has been happening a lot. My categories will have a lot of fiber functors. So they're probably like highly compressible.
But also they won't be abelian. It's also a deviation.
It's a minor point. I think that was set up, right? But you're right. So let's start with the setup. I'll have two major players, a category T. And in fact, various things were already defined by Breche yesterday, which was very nice. So T will be a rigidly compactly generated tensor triangulated category. And then, so basically T is going to be a big category with a nice small set of generators. Inside T, I'll consider a small category, which will be compact objects in T. Let's call it K. And this will be essentially small tensor triangulated category. So they have a lot of structure, but maybe we can just think of a particular example. Maybe the most appropriate example here is if you take your favorite symmetric tensor category, for example, category of representations of a finite group over a field. Let's say, how do you guys call symmetric tensor categories?
C.
Do you use anything else? So D is your symmetric tensor category. We can form the stable category. And this will be a tensor triangulated category. And basically, it's a prototype example for what I want to say. And I want to reserve C for ideals. OK, so this will be the setting. These categories can be quite difficult to understand. And I'm going to try to study them using tensor triangular geometry.
So this is quotient by projective stuff.
Yes.
But you need to, if there are no projective.
We can talk about what symmetric tensor category means. I'll be with a category where I can't take the stable category.
So it's supposed to have enough for that.
Yes. Well, OK. What I actually want is a Frobenius category. And the stable categories I'm going to be taking, they'll be taken for Frobenius categories. I'll have enough projectives, enough injectives, and they'll be the same. And this is the condition that will guarantee that my stable category will have the tensor, the triangulated structure. When I have a very specific example in mind, you can just look at representations of, say, finite group over a field K. OK, so you want to study this category using categories using tensor triangular geometry. And basically, these are code words for trying to understand lattices of thick or localizing tensor ideals. So for the category T, this means that we want to try to understand lattice of, and I'll try to make sure I say thick. I'll define what they are to distinguish my ideals from the ones that appeared yesterday. Chris?
I don't know if you care, but do you want the big stable or the small stable?
I kind of was deliberately trying not to say what S was, and that will probably be the theme of the talk as well. But yes, I want to talk about big ones. Thick tensor ideals in K. So K is my small category. Now in TT geometry language, this is equivalent to asking to calculate what's called the Balmer spectrum of K. So that's another way of expressing the same question. And this is also, if you think about it from an algebraic topologist perspective, trying to answer the following question. If you have two objects, M and N, in your category, when can you build M out of N? And by build, I mean that, so we're in this TT category, it has various operations. Can think about your favorite triangulated categories, but there we can take shifts, we can take cones or extensions, we can take sums, we can take summons, and we can also take tensor products because we're in a tensor category. So these are all the homological operations which are allowed. So we can take shifts, cones, direct sums, summons, and we can tensor. And this is, again, asking the same question. So if we can build M out of N, another way of expressing it, we can say that M is inside the thick tensor ideal generated by N, if we can classify the lattice, or describe the lattice, if we can compute the Balmer spectrum.
So when you say tensor product, it's tensor product with anything else. It's
Yeah.
not just with
So, yeah, and I think I should give a definition. So this is kind of philosophy. Start with the definition, now I'll use C. So I'll say that C, inside my TT category T, is a thick tensor ideal.
What about dual? Are you allowed dual also? Well,
So my category is rigid, and I think duality will follow from what we can already do, but it will be there. Yeah, you take, if you tensor M dual, you get into, or M tensor and dual tensor M, can split it off. So this condition will give it to you. Okay, so C is a thick tensor ideal if one, so my tensor ideals are subcategories. They're not collections of morphisms, they're collections of objects. If it's a full triangulated subcategory, it should be closed undertaking direct summons. And so this is a thick subcategory. And then its tensor ideal, this means that if M is in C and N is any other object in C, then M tensor C N is in C. Since I'm conveniently assuming that my categories are symmetric, I don't have to worry about whether it's a right tensor ideal, left tensor ideal, or two-sided. tensor ideal.
N in T or N in K?
Thank you. We're starting with K. It's nice when people are not asleep, since it's so early. Okay. So this is what we'll try to do. Then with this definition, hopefully it's clear that, or relatively clear, that classifying thick tensor ideals is basically equivalent to answering this question. Like, when do two objects generate the same thick tensor ideal? Or answering this question. Okay, what about the big category? So Chris said I should use K there. For the big category, we also ask the question of classifying localizing tensor ideals. I have to pick which side of the ocean I'm on. I guess I'm this side. In T, now the technical term I'll use here, which probably won't define, is stratify T. So this is something one can define, which is somewhat stronger than describing the lattice of localizing tensor ideals, but this is what we'll actually do, and it implies that we can classify, describe that lattice. And again, one can try talking about this in terms of building, although topologists might object to that because you're building like an infinitely many steps, because this category T is big. But basically, you're still asking when, if you have two objects, when one of them is in the minimal localizing subcategory generated by the other. What is a localizing subcategory? So we say that subcategory is a localizing tensor ideal if it's a full triangulated subcategory, tensor ideal in the same sense, and it's closed under arbitrary direct sums. So in the localizing subcategory, you can add things. You know how much that actually follows. It's a result, I think, of Niemann in the triangulated categories book that in the infinite category, once it's closed on direct sums, then the retract property follows. I guess your motivation depends on where you come from. From the representation theoretic perspective, when we deal with very big categories, wild categories. So, like if you're in the modular setting, I guess what I learned from Eric to say, there's no hope to classify indecomposable modules. There are various questions you can pose and try to answer, but there are just way too many of them. What is trying to classify indecomposable modules? Well, you're trying to classify modules in your abelian category up to direct sums. And that's just too hard, okay? So you cook up your triangulated category, it has more structure, and you try to classify things up to operations allowed in the triangulated category, which is all of those. It's a much coarser question, but that one apparently you can solve. I was told that I can do this, and I'll try.
So the reason one should make distinction between T and K is because you may have infinite dimensional indecomposable modules, which if you use them, you get kind of more.
I think both of these reasons are valid.
Even if you don't have infinite dimensional.
So I'm not going.
I mean, why it's important to consider not only K but T? Because
I can try to answer this question, which is probably not what you want to hear. Even if you're only interested in finite dimensional modules or small objects, there are various constructions that you often like doing. Like you want to have a joints. Various other things where you want to have columns. And then you automatically end up in the big category. So even if you start with a small category, you often want to take some sort of int completion and work there. And this is what T is going to be. But the original interest is in the small category. Okay. So the tool I want to talk about this talk for these calculations is we'll try to compute. So I'll refer to this problem for K as computing its Balmer spectrum. But basically, it's this question, classifying the lattice of thick tensor ideals. Going to try to calculate this. Fiber-wise, in the following sense. So I'm going to hope that my category has enough nice fibers. And by fibers, just mean that I'll have a family of exact tensor functors. And they will be for the big category. From my big category T to some sort of fiber category. The functors are going to be tensor exact. And this family will be parameterized by some parameter space. And then in an ideal world, I'll have both the family, and then I'll have this fiber categories, which are easy and which I probably already understand. And then I'll be able to put things kind of in the local to global way together to get what I want for T. It's like a very simple-minded approach to take what I know and get what I want. And I'm going to list a few examples of this, starting with the examples I'm not going to cover. If you want, you can, one can sometimes sheafify that. Basically, this means that we can consider T as a sheaf of categories over X.
The conclusion here being spec K would be X.
Huh?
The conclusion here being spec K would be X in the way that you're saying this.
You either have to say it a little louder or take your mask off.
The conclusion in this case being spec K is X. That's the idea?
No.
No. Okay, never mind.
I mean, the spec K is going to be fibered over X, right? Okay, examples. So let's start with examples which are more interesting geometrically, because the example I'm actually going to describe in the end, in a way, is like the most obvious one. The parameter space is not very interesting. You guess it right away. And there, the things just work the way you expect once you figure out what you want. So let's start with more interesting examples from the geometric perspective. So the first one is probably P-restricted Lie algebra. So let's say we have a reductive algebraic group, G, over a field of positive characteristic. Then we take Lie of G. And the category of restricted representations of this algebra is always a restricted Lie algebra. Positive characteristic is a nice category, Frobenius category, symmetric tensor, everything you want. You can take the stable category and ask what the spectrum is. And one can think of this category as fibered over the space X, which is the flat variety. In fact, it has to be twisted, but and this goes back to, I think, the work in the 80s by Friedlander and Partial. I think I should also mention Anderson Jensen. And we know what the spectrum here is. Sort of in the same category, one can consider the same family, Frobenius kernels of an algebraic group, a reductive group.
Sorry, can you say in this first example what the functor then is, this F lambda?
Yes, you parameterize, to give you Lie algebra, you parameterize Barthel subgroups by this. For each Barthel subgroup, you have a restriction. That's your functor. Okay. If you have a Frobenius kernel in algebraic group, again, characteristic P, we look at the category of finite dimensional representations. It has a nice stable category. You can ask what the Balmer spectrum is. Once again, it's fibered over more or less the same thing. You have to twist more. That's a formality. And you can compute the spectrum. In case Carolina has a question, the fiber functors are basically the same. We look at the Barthels parameterized by this. And this is the work of Suslin, Friedlander, and Mendel. One can also look at a small quantum group, the root of unity. Again, this corresponds to a finite dimensional Hopf algebra. It has a nice stable category. You can ask what the spectrum is. Disclaimer, we don't know that. But it is fibered over the same thing. You have nice fiber functors, and you can try to get information out of it. And this is the way that Chris and I approached this TT geometry for the small quantum group. But the way basically, and it's just what geometric representation theory tells us to do. Okay. And the example in my title is the one I want to focus on. Oh, actually, there was one more example before I get to that. And this is the first one chronologically. So you guys know what Quillen stratification theorem is. So this is for just a finite group. Oh, geez, this is a finite group. And K is a field, but characteristic should divide the order of G for things to be interesting. This is sort of the classical stable category one looks at. And here, the category is fibered, as Quillen told us, over a finite set. And the set is the set of elementary abelian P subgroups of G. And of course, it does go back to Quillen, but I think in this setting, it's due to Benson, Carson, and Ricker. And when I give references, what I mean is that in this work, this approach was used to actually calculate what you want successfully. Okay. Now, the example I want to look at is the following one. We start with any commutative Noetherian ring. And, well, with an algebra A, which is going to be finite, projective, co-commutative Hopf algebra over R. It's a lot of words, but they imply various properties I want. And also, as we, again, learned from, I think, at least a couple of talks yesterday, this is encoding the fact that we can look at this geometrically. So this A corresponds. Do people see if I write here, or is it too low? OK, thank you. This corresponds to finite, flat group scheme. defined over R. I'll probably subconsciously go back and forth between using A and using G. So if it's not clear at any point, feel free to stop me and tell me to use different player. But basically, I mean, the equivalent. So if I have such a group scheme, I have the coordinate ring. This is by definition, finite means this is a finite algebra over R. It's a Hopf algebra, it's commutative, and A is going to be the R dual. So I'll also use the group algebra notation for A, following what happens for finite groups. So this is a dual to the coordinate algebra in particular. It's co-commutative, and this is where the symmetric thing comes from. Right? If you look at the category of representations, then there's a tensor product, and it's symmetric because it's given by the coproduct. What is the category? So I'm going to look at the category of modules for my algebra A, the same as representations for my group scheme, but they have to be projective when restricted to R. So this is the category of lattices. So G lattices over R. My modules are projective over R. Yes?
Is there some example to keep in mind when A is not free over R?
Yes. So probably won't get to that, but here's an example. I'm not going to get to describe an example, but as happens 95% of the time in this business, if you want an example, what do? You take the Kallen group. So let's take the Kallen group over F2. So you have F2, x, y over x squared, y squared. Take your algebra to be F2, x over x squared. That's your algebra R. And then A is the group algebra of the Kallen group. And so you have a group scheme, which is a very little, tiny thing, defined over this nilpotent algebra. Apparently, it has all sorts of weird properties. But we can calculate its spectrum.
But it is free as a module over R.
Yeah.
Victor asked us, projective, not free.
Wait.
Yes?
Yeah. I mean, since your generality is...
Oh, okay. Then I don't want local. Well, you just take something. You take an algebra which is not local. Take like a direct sum and then define something over that.
okay.
Sorry. I thought my example was more interesting. Any other questions? Realizing I'm not going to get to the end of my talk anyway, so I'm open to have a free discussion. Okay. I also can look at all, so these are finitely generated A modules. Can look at all modules. Again, require them to be projective when restricted to R. Then what are the categories? I can just define, right? I'm supposed to define the stable category, right? Since I'm the first person looking at this definition. So I can look at the big and small stable category. So you can imagine S to be either big or small, depending on what we want to talk about. The definition is the same. So for this category, we take objects the same as objects here, but for the morphisms, and here we take morphisms in the abelian category, in this category. And we mod out maps that factor through projective in this category. So that's the standard definition of the stable category. You can do it for any, say, Frobenius tensor category. And again, this works either for big or small stable category. But you can also think about it in sort of a derived way. We have a localization sequence. So we can look at the bounded derived category. This guy. Inside here, it will have a tensor ideal. Just look at the derived category of A itself. No. That's what I want. When the derived category of projective modules over A, any projective module over A is going to be a projective module over R. So if I have this sitting in there, it's a localization sequence. If I localize, I get the stable category.
I guess in the middle you mean A mod? Just A mod?
Yeah.
Well, in the middle. In the middle.
No, in the middle, I mean taking this category, taking the derived category.
It's not a billion, right?
That's true. I was going to dance around that point, but that's true. You want to discuss that? It's an exact category. It inherits the exact structure from just mod A, and we can take the derived category. But yes, that's exactly correct. Correct. It's not an abelian category. Okay.
Why is it bounded derived category? I mean, there are objects which do not have finite resolutions. Is it okay to take bounded?
Yeah, it's not the perfect one. So it's just the derived category of finite complexes, bounded complexes. Yeah. The thing that we won't get to is that these guys have incompletions. We have big categories they naturally sit in. This one is a stable category. This has an incompletion, which is an interesting category. They won't get to, but one can stratify it. So there is sort of a big world sitting on top, even though it's at the bottom of that world. So the outcome is that we can think about the stable category just this way, or we can actually think about it as a derived category. And in the TT world, these categories are very close to each other. Like the spectra are more or less the same. They differ by just 1 point. We can make one more comment. One can think about it yet.
So this corresponds to Proj construction, this thing. Like when you construct Proj from graded algebra.
I think the answer is yes. So the final answer, and I think I'll state the theorem in a minute before explaining the terms in it, but at least I have the theorem on the board. When we calculate the spectrum, we'll get the Proj here and the spec here.
So when you said extra point is the zero, the origin which you throw away when you define Proj.
Yeah, exactly. One can think about the thing in the middle in more geometric terms. And this probably goes more in line with Brecher's talk. So that category we thought of as G equivariant category on spec R. Then we take perfect complexes. Okay, and maybe that's a better description of what we want to do. And this also leads to why, well, one reason we're interested in this category. This whole TT geometry started with a paper of Paul Balmer in 2005 called something like Prime Ideal Spectrum for Tensor Triangulated Categories, where he introduced what a spectrum of a TT category is. And that paper has 2 examples. One example is if you take a quasi-compact, quasi-separated scheme, any affine scheme is such, so I'll just state affine schemes. So you can take the category of perfect complexes. Oh, sorry. Of perfect complexes over a ring R. Let's do spec R, be more geometric. This is a tensor triangulated category, essentially small. One can compute its spectrum, and this is due to Hopkins. Should probably also mention Neiman and Thomason. And one of the first observations was that if you compute the Balmer spectrum of this category, you get back spec R. So it's a reconstruction theorem. On the other hand, you can take a finite group scheme G over your old familiar field K of characteristic P, take the stable category, that, so kind of what I'm trying to do there, but over a field, so it's much easier, I don't need any projectivity assumption, and also compute the Balmer spectrum of that, and here you get the proj of cohomology of G, which is a result of Eric and myself. And these are the two examples that Balmer gives. Well, this thing is, it gives both of them. It's a generalization. Why? If you take spec R to be a point, then this stack just gives you the, okay, it doesn't give you this category, it gives you the one sitting on top of it. But from the spectrum perspective, it's more or less the same thing. And if you forget about G, then you get this one back. You kind of restrict to both of the worlds that we know.
So what do I first understand right? So this Balmer spectrum, it's always a scheme, or not just a set? Or
It's a locally ringed space.
locally?
It's spectral space, if you want. I think for the very first example in stable homotopy theory, it's not a scheme for the finite category of spectrum. In all my algebraic examples, it's a scheme.
But if you didn't throw away the origin, that would not, then it would be a stack.
Well, I mean, just you have a graded algebra, and you look at all graded ideals. So it's like homogeneous spectrum, the graded
So in the
algebra.
projective space, your variety union with zero, yes?
Yeah.
Which is really a stack more than.
Okay. Fibers. It's kind of obvious what one considers for fibers of this category. The parameter space is just spec R, and for any point, spec R.
This means even cohomology, yes? Even degree cohomology.
Okay, I knew Pasha would ask this question. I was going to get to it later. I'm going to ignore this entirely. You can take even cohomology. You can take super varieties.
Okay.
I mean,
It doesn't matter because the actual topological space.
exactly. I mean, the question I'm trying to solve, it only cares about the topology of the space. So I'm not going to address that point. You can take even if you want.
So it is reduced? Oh, sorry.
Cohomology or
Yeah,
no?
you take reduced scheme.
Yeah, yes.
I can take the reduced scheme. Yeah, I mean, I just care about the Tarski topology of that and the closed or about the sets. So I can reduce my cohomology, yeah. So in particular, cohomology is much more complicated than this classification, particularly because we throw out all nilpotents. Okay, so what do we have? Well, we have these modules over A, which are projective over R. For any point, we just take fiber. So if you have M, A module, your this F lambda just specializes at the point lambda. So I have these functors. I think I'll denote it by mk. Okay. Okay. And I have a whole collection of them, and of course they're parameterized by this. And so my categories can be fibered over spec R. And I have, to put the information together, I have three main ingredients, three theorems which are already known and useful, which set it up for me. So the first thing is that, well, it's actually this one, that if we look over a field, then we can calculate the spectrum. I'm going to use this notation, which is terrible, but so I have my group scheme corresponding to the ring A. I specialize A to a point. I can also specialize my group scheme to a point. Just take the fiber. So this is proj of cohomology. And this is what Eric and I proved. We also have the classification of big localizing tensor ideals. Say it this way, that cohomology in a point stratifies the big stable category. Basically, this means that it governs what happens with the lattice of localizing tensor ideals, or that there is one-to-one correspondence between localizing tensor ideals and subsets of the homogeneous of the proj of this. So basically, we know everything about the fibers, and there is one more recent ingredient, which is actually my favorite part of all of this, and this is a theorem of Kallen. From 2023. And this one simply says that if you look at cohomology, so I'm using G instead of A, but you can also put A. So basically it's the Xth. This is finitely generated. If I were a little bit more proper, I would say that that G has what's called the finite generation property. I need this, and I also need the property for modules. This is a generalization of celebrated theorem of Friedlander and Sussman on finite generation of cohomology.
So there's no conditions on R?
Commutative Noetherian ring, which is a pretty weak condition, I think. Is it true that it's necessary for it to be Noetherian?
Benson has a counterexample.
Okay. Okay, Maybe I'll state theorem, which is not really surprising at this point. We can stratify the category with this cohomology ring. Or equivalently, can describe the lattice of localizing tensor ideals in terms of the proj. An immediate corollary of this, so this is a harder category to deal with, but once you know what localizing tensor ideals are, you can say what thick tensor ideals are in the small category. Chris, you look like you might have a...
Do I need projectivity over R for this Kallen result?
Very good question. So I think if you don't assume projective, don't have cohomology. Because, I mean, we didn't talk about what cohomology is, but like you can think about it as right-derived functor of the fixed point functor. If you think it's not projective, that is not left exact. So somehow the fact that your finite group has to be flat, it's kind of embedded into the problem. Had various discussions with Paul Sabaji about this, because we always say that the finite group has to be flat for this reason. If you look in Benson, he actually defines finite group schemes as flat. They always have to be flat. I mean, it's kind of funny in Benson because he calls rings and fields K, and then somehow he just sneaks in on you when K becomes a field from a ring. And like any reasonable result you want to know, you look it up and it's already a field. But yes.
Are there any examples where it's not flat? Like, is that an interesting question? I don't know.
Probably. Okay, so we can compute the spectrum. It is somehow what you expect it to be. Maybe I'll just make a couple of remarks. Oh, yeah, sure, of course. Sorry, there's no K in here. I guess I just said that Benson calls all his rings K and called it K. Yes. The first remark is that the second result on the finite level was obtained for finite groups independently by Iyengar. And so he's a geometer, so he certainly looked at it from the stack perspective. So for him, G is a finite group. And I should have said from the beginning, I think in this audience it doesn't matter because when we have all this finite, all group schemes corresponding to rings and plays around all the time, but one can always, I mean, it's all interesting if you just take G to be a finite group. And in that case, you don't have to specialize. Finite group is a finite group. Okay, minute. Here, so Ike only does it for finite groups, even though he announced that he can do it for finite group schemes as well. It's not available yet. But his action of G on R can be non-trivial. So it's a much more general result. One last comment. Maybe I should have set up Pasha to ask me this question. But the most unexpected thing in here was compatibility of the fibers. So basically, it's kind of straightforward what one has to do. You have these fibers for prime ideals on R, and for each fiber, you have the corresponding thing over K, and you have the cohomology, and there you have the isomorphism because of this theorem, which was somewhere, that Eric and I proved. And then you put things back together. What happens is that you have to compare what happens to cohomology when you take the fiber outside and inside. And a priori, I mean, at least I didn't see any reason to expect that they compare nicely. But it turns out that if one actually looks at Kallen proof, which followed an old idea of Dave Benson and David Haberger from '87, just over Z, then one can figure out that this specializations, taking fibers on cohomology inside and outside, is what's called like a Quillen isomorphism. It always induces an isomorphism on spectra. Whatever your ring is, it's always an isomorphism on spectra. And this uses finite generation of cohomology in the proof. And so once you have that, then you just put things together and it all works. Oh, right, I promised to mention Deline. So Deline in this picture, so he proved basically that there is a projectivity test in this world. That if you want to check that something in the stable category is projective, you just look at the fibers and check that it's projective over all the fields. Then it's projective. So it's kind of this fiber functors, they're jointly conservative due to Deline. Okay, I'll stop.